Marusa.
Not. Ah. Cool. This is handy. Okay, I'm giving away everything too. Fantastic.
All right. So, good afternoon. This is going to be probably a little bit different style of team talk in that Bryce basically suggested that we do this, and we couldn't think of any coherent topic that we could both talk about. So you're actually going to get 3 separate talks back to back to back. So we'll be talking first. Nothing really new here if you've been following the literature religiously, but thought I'd give everyone sort of an update on sort of the current status of the bullet cluster and the other known, well-published merging cluster, ABL 520. And then Marusa will take over and talk about her new cluster, which we haven't yet come up with a good nickname to stick with it. And then lastly, I'll come back and I'll talk about a completely different idea, which is how we can measure tomography using only clusters of galaxies, and how you can do this even if photoz's wind up not working, which is the main reason for thinking of doing this. All right, so the bullet cluster is, of course, a merging cluster. It gets its name from the supersonic shock front over here. When basically we published a paper a year and a half ago that basically showed the offset, and our conclusion was you could not reproduce this system using alternative gravity without having at least twice as much matter sitting over here on the galaxies as you had baryonic matter sitting here in the plasma clouds. Right? And people who have tried doing this using Tevez basically agree with us. So Angus et al. Tried this, and they came up with they needed actually 2.5 times as mass sitting here on the galaxies as they had sitting in the plasma. And this was for a very particular model of Tevez, and these groups down here tried to do it for a more generic set of Tevez models, and they came up with basically the same agreement. And to my knowledge, nobody has yet come up with a way of doing this without having at least twice as much mass sitting there on the galaxies. So we're basically using this as our proof of dark matter. You might also be able to see, if I go back here, we don't have a stick, but well, yeah, no, a stick is better for this. But if you look here at the main cluster, probably easier down here, and you put a line going perpendicular to the gas cloud and just look at the contour spacing, you'll see the contours are much more spaced out across the gas cloud than they are in the other direction. So we are actually detecting the X-ray plasma in the weak lensing, but we're detecting it as a perturbation on the main lensing signal, which is exactly what we would expect if the plasma makes up about 15% of the total mass of the cluster. Right? Angus et al. Actually did something a little bit even clearer, which is they took this line here connecting the centers of the 2 galaxy distributions, and they subtracted the southern half from the northern half. And this is the residual, with this thing being that and that being this. And so these are actually the plasma clouds that they're picking up here. Right? So we not only have proof of dark matter, we can actually now confirm that baryons have mass.
So lensing, is a lensing one?
Yes, yes. This is the red dotted lines here are just the contours that we published, and all the other lines are their models using Tevez. All right, now the claim up until at least a couple months ago was that even though you needed dark matter here, that maybe you didn't need a new particle. You could do this with existing dark matter, in which the idea was that you could use a 2eV neutrino, and that would get you just enough mass to explain what you needed on clusters without the dark matter clustering and screwing up the good Mond agreement for rotating spiral galaxies. Right? I'd already pointed out that actually the bullet itself is too dense for a 2eV neutrino to work, and you can also take almost any cluster of strong lensing and show that those are too dense for a 2eV neutrino. And so currently I believe they're coming up with this idea of maybe you can hide just enough baryons to somehow get this to work. They haven't yet really explained how they get by the Big Bang nuclear synthesis problem. All right. The other important thing, of course, to remember is that dark matter is now officially blue. So if you put out press releases, don't confuse people. It's blue. All right. There was another problem that showed up a couple months later, which was once we published our mass models. So these are sort of the best fit values. We get about 2.2 kiloparsecs for R200 for the main cluster and R200 for the subcluster is currently sitting at 1 kiloparsec. This is definitely an underestimate of what the cluster was beforehand. We're guessing it was probably about a 3-to-1 mass merger to start with, maybe 4-to-1. All right, so you take this and you compute the infall velocity. It should be about 3,000 kilometers per second based on the systems having passed through each other and are starting to move away again. And then you can go back to that X-ray shock and you can measure the shock velocity based on the sound speed and the Mach number of that shock, and you get 4,700 kilometers per second. This was pointed out as a possible problem and then was latched onto as maybe evidence for alternative gravity because that would have a faster infall model. Turns out there were two things that everyone was forgetting about, including us, when we first published this paper. Actually there's three. This one I didn't forget about, but I just didn't mention in the paper, which is we've already known from in-body studies that weak lensing, the projected mass which we use, we're always fitting spherical mass models. And if you have a triaxial cluster, depending on whether your major axis is in the plane of the sky or along the line of sight, you're going to be systematically underestimating or overestimating your mass. And if you allow major mergers in body simulations, tend to occur along the major axis of your cluster. In this case, our major axis would be sitting in the plane of the sky because that's where our merger is occurring. And in those situations, the in-body simulation suggests that we underestimate the mass by about 30%. So this would take us from about 3,000 kilometers per second up to about 3,500 kilometers per second, which would help, but it's not quite completely there. And then the other two effects were pointed out first by Mila Slovevich, in which he pointed out that we're actually measuring a shock velocity, not the velocity of the particles in the shock. And the shock velocity is not affected by gravity. So we're not measuring the current velocity that the balloon is moving at, we're measuring the maximum velocity that it had. All right? And then the last one was pointed out by Springwell and Farr, who pointed out, go back to the picture here, that what we think has happened is this subcluster over here started off down here, it came up along this angle and sort of got bent over as it came through, slightly missing the center of the cluster, which means that the X-ray gas right here has been feeling a steadily increased potential throughout the course of the collision because this extra guy has been continually moving towards it. Which means this gas, which used to be in hydrostatic equilibrium, is now in a wind moving towards the center of your cluster. And based on in-body simulation, what Wolfer Springel calculated was for these masses involved, that wind would be about 1,000 kilometers per second. So you come up with all those, and that means that the true velocity that the shock is moving at, when you correct for all this, is somewhere in the 3,000 to 3,500 kilometer per second range, which is exactly what we would expect from the mass estimates of the weak lensing. Right? So there really isn't a merger velocity problem. It's just that we weren't looking at what everyone thought we were looking at. All right. We've also recently found an interesting strong lens. Marusa actually published this in her paper. At the time, we had a I-band image which might have showed a hint of this lens, and we had the IRAC images in which you can see here are two sources, here are two, A and B, as they're listed. So we looked at this, we said, well, it might be there in I-band. It wasn't there, it definitely wasn't there in some 606 HST imaging that we have. So we were saying maybe it's a Redshift 6 high lens. We then got some MIPS data, shows up very strong in 24 micron, and we also got some ground-based infrared, which is completely not there in J or K. So after briefly flirting with Redshift 22, we then pulled back and did an SCD measurement, and what we found was that it winds up being about a Redshift 2.7 LERG is the best fit for the scene. Right? Now, of course, we don't have any spectroscopy for this. And at the same time we were figuring this out, another group led by Grant Wilson pointed the Aztec submillimeter camera at it and found that these two sources combined to give you a 16 millijansky submillimeter source. Right? Those of you used to submillimeter will know that 16 millijanskys is very, very bright. Right? This is one of the brightest submillimeter sources on the sky. Right? I should mention that actually in these images up here in these two blocks, we've subtracted out a cluster galaxy, which is responsible for the splitting of those two into two separate images. Right? We then remembered that we actually had a strong lensing model for the system after some prompting from Jean-Paul Knib, and Marusa went and took the location of these two and predicted that there would actually be a third image fairly nearby. And so we went and looked in Spitzer data for that, here are two images, and there's where Marusa predicted the third image would be, and there is something there. It's much fainter, right? Not nearly the same magnification, but it does have the same color ratio, at least in the Spitzer data, right? So we think this is probably the third image, which gives us a pretty good idea that the strong lensing model is pretty good for this cluster, which at some level is somewhat amazing because all of the strong lensing constraints that we had were way up here. Right, so even those strong lenses could help us get this thing correct. All right, so that's
it
sort of
didn't
the
land
bullet
right on the top, but
Sorry?
it landed more like
It is
where the
good.
C
Yeah, okay,
is, or you
fine.
go further.
It goes on by half an hour a second. It's strong lens. All right, so that's sort of the bullet cluster. As far as conventional CDM, there's still absolutely nothing surprising about it. All right. Here's the other one, which in terms of conventional CDM, there's something is surprising about it. This is from Madavi et al. This is the Abel 520. And what they found was they went and did a weak lensing mass, and Abel 520 has a group of galaxies up here, which has a CD galaxy in them. Has a group of galaxies over here, which also has a CD galaxy in it. There's a group of galaxies down here, which I haven't yet found a CD galaxy. It looks like this is probably a poorer cluster. And there's some more scattered all over here. The X's are all known cluster members from, I believe, one of the CNOC surveys. And you can see it's scattered all over the place. This is, and then here's in pink is your X-ray measurement, from which right there is the only other known supersonic shock front in the X-ray, but it's only Mach 1.3 and within errors of being subsonic. So we're not entirely sure still. But you can see from this, there's not really a central plasma cloud. It's all over the place. We think this is probably 4 or 5 separate smaller clusters that have come together over the past couple of billion years, or are in the act of forming a giant cluster, but are still nowhere close. There are two unusual things about this reconstruction here. The first is there's this large group of galaxies over here that they don't pick up any weak lensing mass for. The second is there's this plasma cloud here which doesn't really have any galaxies around it, for which they get a phenomenally large amount of mass. Right? Now, they're not the only ones who have published this. In fact, using most of the same data that they used, earlier a Japanese group published this as well. And you can see that they pick up that northern group of galaxies here. They picked up that eastern extension over here. And you have the southern group here. They have a little bit of excess around the plasma, but not really much. And then I have some separate data that we actually got from Magellan at the same time that we took the bullet cluster data that I have never quite gotten around to publishing, which we again have the northern group of galaxies, we have the eastern group of galaxies, we have the southern group of galaxies. I don't know if that's actually real or not, but those are all cluster galaxies over there as well. And we do have a little bump on top of the gas. That's, again, consistent with only the level of 15% of the mass being in the gas, and that is simply being the largest noise peak sitting on top of that bump. So the question is, at what level is Madavi's bump larger than everyone else's? And the answer is typically 1 to 2 sigma. Right? And this is a recurring theme in weak lensing when we're looking at clusters, which is the bullet cluster uses the entire weak lensing signal. This is trying to use a small little subset, and we still have not yet come up with a very good way of measuring what is the true noise level of a small little bump sitting in the midst of otherwise a giant mass distribution. All right, so, and as per, this is I think the 4th dark bump that's been reported. The other 3 have all gone away when we've gotten better data. So this one, I think Madavi is actually getting some HST data sometime this fall. And so when he looks at that, we should get about a factor of 2 more galaxies. And so that will improve the statistics a little bit, and at least it will push it up to whether there's a 3 sigma difference or whether it goes away. All right, so I'm not convinced about this dark bump. I think he's just basically getting the plasma plus some noise. All right, so I'm going to stop here and let Marusa take over with her new cluster.
All right, thank you. So I want to apologize because I've been coming down with something nasty lately, and so I might not be as excited about this as I usually am, but that doesn't mean it's not exciting. I'm very excited about this cluster. So for those of you who know me, I usually study those big things. I like the big pink elephants, and so that's why I am starting off with this slide. And today I'm going to talk about a very special one, which I call a baby bullet. And my collaborators, which are listed here, they all went crazy and said, well, you cannot call it a baby bullet. Why not? Well, it's neither a baby, because it's neither small or young. It's a big beast. And it's not a bullet, because it doesn't have a bullet, and I'll show you why I'm telling you this. But I still like to call it a baby bullet, and after much of discussion, we didn't yet come with a better name. So, well, somebody suggested to just use the real name, which is Max JO25 minus 1222. But then, you know, when you're super excited about something and you really deeply care about something, I mean, you don't just give them the numbers, right? You wouldn't call your daughter M0901, right? You give it a nice name. So I still call it a baby bullet. You will hear people raving about, but yeah, the other idea was to use an acronym. And given how good we are, astronomers, in finding good acronyms, I said no. This is one thing I veto. So I don't know if this is really going to be beyond the obvious, well, as much as pink elephants can be beyond the obvious, but so this is the bullet cluster, the way Doug showed it, and it turns out this is now strong and weak lensing map, and in blue, as dark matter is blue, it's actually the total matter, and maybe you can see it that with good strong lensing data, you can actually start to probe the structure of those clusters, and you can actually start detecting gas and individual structures in this cluster. What was so great about the bullet cluster was that we could actually measure the properties of dark matter. And the way we do that is, well, first we combine Chandra data with lensing mass maps, and so this gives us constraint on dark matter self-interaction cross-section. The way it works is, these were two clusters that collided in the past. And so, because we know that gas is collisional, it behaves like a plasma, it gets stuck in between. The fact that dark matter clumps are following galaxies which are effectively collisionless allowed us to give to make upper limits on self-interaction cross-section. There was significant offset between subcluster X-ray gas core and dark matter peak, gives us the first limit. Then there is survival of subcluster. Imagine dark matter being collisional. If that was the case, the two clusters would merge, but they wouldn't retain their peaky structure they would at least puff up in a little bit. And there is also no loss of mass. If you would have dark matter which is collisional, when those two clusters collide, you would actually start losing mass from those two clusters. And the way we can see this is by looking at the mass to light ratios, which remain fairly consistent with whatever the relaxed clusters are showing us. So this gives us a final constraint when we run full-blown simulations by Scott Randall et al. The paper is meanwhile published. Sigma over m 0.7 centimeters squares per gram. If there are any particle physicists in the audience, this is 1.3 barns per GeV, which is huge, but it's not huge for astronomers because the dark matter required to explain the substructure problems was given the limits that one needs is sigma over m is 0.5 to 5 centimeters squared per gram, and we basically exclude most of those limits. So
do you also constrain slowing coming from, so slowing coming from, the dynamical friction, of the two subclusters on each other?
because these are just order of magnitude estimates, whereas this number actually comes from simulations. You take your two clusters, you smash them together, and you look what happened to them afterwards. And you have a good idea of what the system has to look afterwards, including all the dynamical information. And you know what the cluster core look like. And so if you assume some reasonable model of how they looked before they collided, you can actually get a proper limit.
Basically, from the centroid measurements of the lensing, we know there's not a large tail of dark matter sticking back behind the bullet.
Yeah.
And so any dark matter that has been tidally stripped off has also been completely absorbed into the dark matter cloud of the main cluster, or scattered into diffuse sheet. And which is what you expect from the less bound outer particles, but not from the core itself.
And it hasn't slowed down much, that was you're saying.
Right. Yeah.
Yeah.
It's moving. Well, it's slowed down just as much as the galaxies has. So it's been affected by tidal friction and only by tidal friction.
Yeah. And so, this gave us a nice result. Everybody was happy. Dark matter was collisionless, and until the Able 520 came, and Doug already mentioned this cluster. And actually, Madavi et al. Went as far as to trying to explain this, what they call a dark core, which is right here, by saying that one of their possible postulation was that in order to get dark matter where the gas is, but not where the galaxies are, is that dark matter has to be collisionless. And their limits are 3.8 centimeters squared per gram, which is higher than our bullet limit, smack in between the Spergel and Steinhardt predictions. So what is going on? Well, the only way to really tell is to find more bullet clusters. And so we found the baby bullet in a search for bullet cluster survey, which is basically just what we did is we took the max clusters, which all had Subaru data, Subaru ground-based data, so you have very good idea where the galaxies are. We also have snapshot Chandra images, and so you know where your gas is. And so you look for clusters that are two-component and have gas located in between. It was actually Steve Allen and Harold Ebeling who did all this search. So we found the baby bullet, which is actually two subclusters at the same redshift. There's also abundant redshift data that comes with these max clusters. And we also took new HST data. We have VIF-PIC2 for 450 band, and we have these two ACS bands, which are really crucial to do strong lensing analysis and also to do weak lensing analysis. Because it turned out with Scott's simulation, what is really important is that you manage to reconstruct the core of the clusters really well. And this is something weak lensing cannot do very efficiently, and so that's why it's crucial that you have strong lensing. In addition, all these max clusters are the sort of a right redshift that you expect them to have strong lensing, and so that's why they were so useful. So we have 3 strongly lensed systems, and then we went afterwards and actually measured one redshift spectroscopically using CAC. So the cluster, baby bullet, has 2 galaxy concentrations. Actually, this one has a single dominant galaxy, I call it BCG3. This one actually has 2 galaxies which are equally bright within the error, so you cannot really say that one is BCG and the other one is not. We just call them 1 and 2. But they're 2 compact structures, and actually if you measure the redshift of these BCGs, you figure out that the 2 clusters are at the same redshift, 2 subclusters are at the same redshift. The velocity separation of the 2 BCGs, so if you average the bottom 2 and compare with the upper one, is the redshift difference is 0.0005 plus or minus 0.004. And so they're really located at the same redshift. And if you interpret this as a peculiar velocity only, you get the velocity difference of the 2 structures in radial direction to be 100 kilometers a second, if at all. And so it's likely to be plane in a sky merger. There is no real radial motion. The 2 subclusters have similar richness and stellar mass, just like any average massive cluster. What I did here is I measured the projected stellar mass in a cylinder of a radius of 300 kiloparsecs, southeast, this cluster, northwest, that cluster, and we get sort of a normal values. So redshift distribution, we have redshifts for around 200 objects in a field, not in an ACS field obviously, but in a bigger field. And we measure the redshift distribution and the velocity dispersion of approximately 800 kilometers a second. there is no real sign of any substructure going on here. Nothing is significantly detected, even though you might think those two peaks kind of, but they're not actually real. And there is definitely no such thing as one concentration of galaxies with a different redshift from another concentration of galaxies. So this is the velocity data, X-rays. So these are the X-ray data, and this was of course no surprise. We selected those clusters to have X-ray offset from the galaxies. And now you see the galaxies here and here, and you see the X-ray data comes smack in between. This is 38 kiloseconds Chandra data. If you remember the redshift 0.58, this is fairly shallow. So we can detect the gas peak, but in order to see a shock front, a much deeper data would be needed to do that. And so the reason we are not seeing anything like in a bullet cluster, like the shock front in a bullet cluster, not the bullet, is probably simply because our data is too shallow. I'll say something else. Okay. So, why is baby bullet not a bullet? Well, the bullet cluster is a merger of a low entropy gas core, which is a cool core, and a non-cool core cluster. So when you merge two such clusters together, the cool core is likely to survive, and so you see this prominent bullet-shaped type feature in the gas of the cluster. Baby bullet is not a merger of two such things. Baby bullet is rather a merger of two non-cool core clusters, which is also this is all very generic because approximately, I believe, a third of the clusters have cool cores, and so it's nothing too unusual that we are seeing here a slightly different type of a merger. But if you remember, this is now back to the big bullet. So this is something we will never see because there is no such thing as a cool core. But the shock front in the bullet cluster is actually up here. And so the shock front we are still likely to see because we expect this merger to happen at approximately, given the mass is approximately 2,000 kilometers a second. And so with deeper Chandra data, that might be it. Now, where is dark matter, of course? That's a big question. And what we did is, again, we used a strong and weak lensing reconstruction method. I need to do the way we do this is we parameterize potential on a grid, and it's sort of non-parametric, but not really. We just like to keep things as general as possible, especially for those merging clusters. You cannot really assume NFWs or anything. It's not likely to be the case. And so it's still the very same old method I've been telling you a lot about in the past couple of years. What happened recently is I'm starting to actually do the adaptive gridding, but not for this project yet. But if anybody has good suggestions on how to do adaptive grids, please see me. Strong lensing information. So what I'm going to show you now is there are three multiple image systems. One I call AB, just because it's a double, and then B and C. And I'm going to show you the images. And so this is a C, and this on top is the 555-814 ACS data color composite. This is F450 555-814 color composite from HST. And so we have this 2, this 3, and then we have this dot, and I don't know how well you can see this dot and a comma, this dot, and that. It looks like commas. And we went and looked at this cluster with CAC, put LRIFS masks on all these objects. We got a redshift of this one. It's at redshift 2.38. We couldn't get any other redshifts, and this is really the limiting thing for this project. Besides the shallow Chandra data is also that the redshifts are really uncertain. And there is much more in terms of strong lensing going on, but it's just really hard to tell, and you cannot, you cannot really use it unless you have redshift properly. So these are the systems, and now if you kind of look at them the way they are curved, and the way they go around, and you probably, if I quickly go back where these are located, so these are the three these are the two, and these are the two. You probably know where mass distribution is going to end up. But let me first show you about our weak lensing analysis, because we used ACS 814. We have two orbits, fortunately, which is our primary weak lensing band. The procedure basically follows the Cosmos procedure. Richard Massey did the analysis, used RRGs, and we used the color information to exclude likely cluster members. Now, originally we also thought we could do weak lensing with WIF-PIC2 data, but we were worried about CDE effect, and so that's why we actually went and also imaged a globular cluster, also for some other clusters we looked at. And this is a globular cluster image taken with WIF-PIC2 at approximately the same time as the other observations were made. So, well, Doug claims he can do it, possibly, and I'm just saying good luck. So we've been the idea to use WIF-PIC2 data for weak lensing. And this is the main result, total mass distribution. This is now dark matter, which is red. Sorry, Doug, but it just doesn't look blue. Blue just doesn't look good on those things. And so what I'm showing here is the kappa contours, and this is the error bar, the position, peak position with the error bar. And you can see that they line up nicely with galaxies.
Why is the arrow much larger in one direction always?
Sorry?
Why is the arrow much larger always in the same direction?
So the reason why it's much larger in one direction than the other probably comes from the way the strong lensing is pointing at. So these errors comes from many different things. The way I calculate these errors is first bootstrap resampling weak lensing catalog, then bootstrap resampling strong lensing catalog, meaning you kick out one image system at a time. Then you look at what the redshift errors, what effect the redshift errors have. There's a lot of things that go in to look at these error bars. So I don't have a good idea, but I'm guessing that's what's
Yeah,
happening.
it's also not unusual. The errors on the contours for the whole cluster, you always have one direction is much larger than the other. It's just the mass distribution, basically.
I mean, you can kind of see that they kind of follow the mass distribution too, but not really. So yeah, I don't have a good answer to this. If I overlay the light distribution, this is now the light distribution, it lines up nicely with the total dark matter, and this is the gas. And now this is the error bar on the gas peak. So you can see they're clearly offset from each other, and they're offset at the significance of 4 sigma. So assuming Gaussian errors from lensing and top hat from gas distribution, because Steve convinced me that there's just no way you can have a gas peak outside that cross, you get a significance of the offsets to be larger than 4 sigma. So here we go, another bullet cluster. And that's why the cluster got named the bullet cluster, because the configuration is very similar to the bullet cluster. So I went a little bit further. The problem with this, as I said, is that we have limited redshift information on strong lensing, and so mass shift degeneracy here still kills you a bit. So you will see that whereas the peaks are very well determined, the mass distribution is not well determined at all, and you will see this reflected in a fairly large error bars. But what I'm showing here is I looked at the properties of this cluster in this cylinder, and in this big yellow circle, just to see what the mass to light ratios of the clusters are, to see what the global properties are, so we are not doing something terribly wrong. So if you look at the southeast, around BCG1, the total mass is 2.5 times, and now you see why the large error bars, times 10 to the 14 solar masses, whereas on the northwest is 2.6, so it's similar mass clusters that we are talking about here. Galaxies sort of at a percent level, just as you would expect. And if you look at the so-called global properties, I mean 500 kiloparsecs is not really global property, but this is where our data extends and also where the X-ray data extends. The total mass and the gas and the galaxies all go in a sort of a, if you look at the ratios, gas is 10% and galaxies are of the percent level. So we are dealing with the normal type clusters, gas around 10% and stars around the percent level. They have a fairly normal mass to light ratios, 70 and 100, slightly on the higher side, but the error bars are huge as you see. And the two clusters also have a normal stellar to total mass ratio. So significant offset, let's figure out what the dark matter is doing. Is it collisionless? Because we don't really have velocity information. So as I told you, we don't know the shock velocity because we cannot see the shock. Things get a bit more tricky here. And the only thing you can do is, you can say because of the significant offset, scattering cross-section for dark matter particles has to be less than 1. And so you can, and this is scattering cross-section, this is the surface mass density of the two colliding structures, and this is the cross-section of dark matter. And so this, you can actually give the upper limit on this number, and this is this number of 4 centimeters square per gram, which is not great, but if we actually had, if we actually could do these two points, it would have been much better, and so we could get a better constraints on the cross section. And so I hope I convinced you that the baby bullet has this similar usefulness as its big brother. No bullet is likely to be seen. We need deeper Chandra data to get a shock front, which is likely to be there because you just need a substantial velocity in order to strip off the gas the way it was stripped. Dark matter self-interaction cross-section is small, and well, this was fairly obvious results, but let's search for more cluster, and we are doing exactly that. So, okay, Doug said dark matter is blue, so I'm going to show you this picture. Yes, dark matter is blue. But we have more of those, so keep in touch. And I know that at least one of them is going to be presented at this conference. So I'm going to do a little bit of advertising. This is Sydney Conference on Gravitational Lensing. So if you want to come to Sydney, it's going to happen between September 29 and October 3rd. The deadline for registration of the talks has officially expired. However, I talked to the organizers, and they said they'll let the people of this conference still submit their talks, as long as you do it still today, so we can go on and start making the program. Thank you very much.
I should mention that, that between Marusa's MAX programs and another program that we have that's looking mostly at Abel clusters that are known to be merging, we should by this time next year have probably 6 to 8 or more clusters that probably neither of them or none of them else will be quite as good as the ones that we've shown, but they all will show galaxy plasma offset. So we'll have quite a few clusters that we can figure out whether or not Abel 520 really is the anomaly with those, with the Manavi results or not. All right, so I'm going to now spend the last 10 minutes talking about something a little bit different, which has mostly been prompted by my trying to come up with ways to do various dark energy surveys for the past 6 months, and getting more and more depressed about certain aspects of them. Whenever I give these talks, Boov always tells me he also gets very depressed while listening to them. So to try to help that, I'm going to give the rest of this talk in what's called the fun theme in Keynote. All right, so what we're talking about here is just standard tomography, right? So for those not used to working in weak lensing, this is just the idea that if you take a relatively high redshift lens, the strength of your lensing signal goes as basically the distance between us and the lens times the distance between the lens and the source divided by the distance between us and the source. So if you look at, here's a redshift 0.8 cluster, here's a 0.5 cluster, here's a 0.1 cluster. You see the 0.1 cluster quickly maximizes out in a signal strength per unit mass, whereas the 0.8 cluster continues to rise completely across this region where most of your background galaxies are going to lie. And so if you can somehow isolate your galaxies into various lens planes, you can just simply measure the growth of the signal, and in doing so, you can get these angular diameter distance ratios. And from that, ultimately, you can reconstruct cosmology. So this is the idea of tomography. So you're simply using the growth of this lensing signal to measure A of t. You can do this in two ways. Wayne Hu, I think, was the first one to suggest in 1999 you could do this for a full cosmic shear survey, which in this case you're looking at both the change of the power spectrum and the growth of the shear signal sort of simultaneously. And then Jane and Taylor in 2003 suggested you could also do this a bit more directly, removing the effect of the growth of the power spectrum by just simply taking the ratio of lensing strengths around known lenses. Right? So here was Wayne's idea. You just simply take your two distributions here. Your higher redshift galaxies still lens everything seen, or are lensed by everything seen in the lower redshift, so you get these two. And you can take your two power spectrum, you can cross-correlate them, and in doing so, you can pick up both the change in the power spectrum and the growth, right? This is basically the idea that all of our dark energy lensing, our weak lensing surveys are based around, right? And here are some of these surveys, right? This is from a recent review from Henk and Boove, who were wise enough to put greater than signs by all these starts. And I don't believe any of these are actually on target, except for below this line, which haven't even started to be planned, really, in terms of the actual building. But you see here are the standard ones. And this, of course, is the standard bias of the person writing the article, which in this case I will attribute to Hank, in which I will correct it a little bit, as there are actually 3 JDEM proposals, which still haven't, and actually possibly more, because the open announcement hasn't come out yet. But so this is this whole idea. We're basing all these surveys around this idea. And there's 3 very large problems with this idea, in that if we had this data right here, right now, we could not analyze it, right? So first of all, our smearing corrections for weak lensing simply aren't good enough right now. This is a known project. The weak lensing community is very vigorously doing this. Sarah is running a very large program, which I think she talked about yesterday. They are improving. I don't really see any technical stumbling blocks that are going to prevent us from getting down to the needed level. So I'm optimistic about getting this correct. All right, the next problem is really more of a theory problem, which is that everyone who goes through and tries to come up with ways of doing this usually makes the same assumption, which is that when we actually measure the shape of a galaxy and do the PSF correction, what we get out is the reduced shear, which is the shear over 1 minus the convergence. Almost every theory paper that I see works with the shear, right? For a galaxy cluster, you can actually measure the convergence directly and do this conversion. For your typical large-scale structure, your convergence is on the order of 0.01. There's no way in which we can actually measure that for any single structure. And therefore, you're going to get on the order of about a 1 to 2% error in your shear measurement, which is going to be a systematic biasing if you simply make this approximation. I know Boove wrote a paper about this, I think last year, in which I think the basic conclusions was this is a problem. No? Okay.
Nice.
Right, and then also, yeah, when you do this, currently this is done for the modern cosmic shear surveys, which is fine, because the level of accuracy of the current cosmic shear surveys is much smaller than this. But the idea of all these really, really large surveys is that we're beating down the shot noise, and so we're getting down to the point where this actually becomes important, right? This has already showed up in that the Sloan surveys, right, the Johnston and Sheldon results, in which they stacked clusters. They were looking at clusters whose highest kappa was 0.02. But they were getting these things down to signal noises of 50. And so if they didn't make this correction, they would have been off by 1 sigma in their measurements.
But this can come out of the n-body simulations.
Yes, that's my second point.
Right. Okay.
But prior to this, everything that we've done prior to this would be making a measurement and using an in-body simulation just to check that that measurement was valid. If you leave this in here, we're now using the in-body simulations to calibrate our signal to get our cosmological results. And in doing so, you're now needing your in-body simulation to be correct.
No, can't you just measure the G power spectrum? And then
Well, like
predict
I said, this is something that I would like to see a few more theorists work on.
That's just a
It's-
technical problem.
What?
It's just a technical problem. You have to correct for it.
Yeah, but how do you correct for it when you don't know what it is around any single galaxy?
I mean, that depends
Yeah.
what you're doing. If you're, say,
Yeah.
comparing gamma spectra or doing parameter
Right.
estimating for gamma spectra. Whatever means you use to make that theoretical prediction for gamma work for G. It might be a little more trouble, but you can use Halo model, linear theory, n-body.
Okay, well, in terms of predicting what these really large surveys are gonna do, I would like to see people go to that little more trouble.
Sure.
Fair
Okay.
enough.
And then the last one are we need these redshifts in order to do the tomography in both ways, right? And really, to get down to these really fine levels, which we're trying to predict for W and W prime, the photometric redshifts, we can accept that they're not accurate, right? We can accept a scatter. What we can't accept is that they're biased. So if the photometric redshifts tell me that I take a sample of galaxies, all of which are predicted to be at redshift of 1, I can allow those to be varying between 0.9 and 1.1, as long as I know what that variance looks like. I can't allow those to actually have an average of 1.01. And to get down to the levels that we need, we actually need it down to be accurate to about 10 to the minus 4, which is 2 orders of magnitude better than they can do right now. And we're not really improving on the data which we're giving them, because you have the Cosmos survey, which is a bunch of broadband filters between K and U, and that's exactly what we're going to be giving them for these surveys. So can you get 2 orders of magnitude just out of improving the techniques without improving the data which you're giving them? It's not clear to me that you can. And so this then led me to the idea of what can we do if this in fact doesn't work, right? So if we look at the total number of galaxies that all these surveys are doing, right? Ignore these lower ones down here, but these sort of ultimate surveys up here, they're all coming up in the range of a couple billion galaxies, all right? There's no way that we can go out and get spectroscopic redshifts on a couple billion galaxies. So for those photo Zs, one of the primary problems with them is that they're looking for basically things like sharp breaks to be moving across the broad photometric bands, which for elliptical galaxies is actually pretty good. There probably is a subset of galaxies for which we can get down to that 10 to the minus 4 bias level, right? But it's probably less than 10% of our total sample. And so in that case, we need to reduce the number of galaxies that we're going to be measuring dark energy with, right? The other way to do it is try to reduce the number of galaxies to the point where we can actually go out and get spectroscopic redshifts for everything.
Are they too faint?
What?
Are they too faint?
For most of them are right now, and so mostly with this I'm eyeing the 20 to 30 meter telescopes, which we should then be able to push down. For instance, for SNAP, yeah, these extra 50 that they're picking up, we have no hope. Okay, even for Destiny, which is going down to these, it's probably hard. If we're forced to rely on spectroscopy, we're probably limited to a surface density of maybe 30. All right. But it is possible. Now, if we have to do that, right, and we have to drastically cut these numbers down, what we want to do is we want to boost our signal. And the way in which we do that is not do a blank field survey, but instead we just simply look at clusters, right? So if you just look at clusters, we still need the accurate PSF corrections, okay? We can now measure kappa directly, so this helps get rid of that a little bit, all right? But the primary advantage that clusters have is there's a fairly large region around every cluster in which the shear is on average 10 times larger than the cosmic mean. This means that for the same signal to noise around these clusters, you're effectively doing a 100 times larger blank field survey. All right? So I went back to a high redshift cluster sample, the only one that I know very well, which is the eDisk survey. This comes from a 135 square degree Los Montañas distant cluster survey. We went and we found 20 clusters from which we estimated, based on the completeness of Los Montañas, that we got about 2/3 of the total number of high redshift clusters. So I corrected my estimates up by 50%. And then taking this survey, I looked at the direct shear measurements that we had and asked over what area of the sky do I have this 10 times higher than cosmic mean signal? And the answer wound up being 0.2% of the total sky area covered by that survey. Okay, so that 0.2% is basically giving you 2% of your total signal. Your noise is going to scale as the square root of your area because it's just shot noise. And so 0.2% of the total area winds up giving you 4.4% of your total noise. So your signal to noise, just from using these clusters, winds up being 44% of the total signal to noise from a full tomography survey over the entire sky, right? If you're using all of these clusters, which you can find. Right now, of course, we couldn't do this because we don't have these clusters, but we do have all these SZ telescopes coming online that are promising to find every cluster, you know, within a redshift of 1.5, at least down around the South Pole. All right, and the advantage of this is you're only using 0.2% of the sky. So you're taking your 2.5 billion galaxies, which the LSST is going to survey, and you're taking these down to 5 million galaxies. And 5 million is a doable number of redshifts, right? It's 100 nights on a 30-meter telescope, but it's doable, right? Whereas 5 billion is simply not doable. So I think it is actually possible for us to do it this way, and all that you lose is a little bit more than a factor of 2 in your final error bars.
So is sample variance a problem for you here?
Hmm?
Is sample variance a problem for you?
Chaos.
How many clusters are you planning to look at?
If you take the LSST, there's 20,000. So for this, from this 0.2% of the area, this also winds up giving you 1 cluster per 6 square degrees. So 20,000 square degrees gives you about 3,500 clusters to work with.
And it's scattered over this.
Yeah, and they're scattered over your survey region.
And how many redshifts are you in total?
I basically for these measurements, I'm keeping those same number densities that we saw.
Mm-hmm.
So taking again the LSST numbers, I need 30 redshifts per square arc minute, which means for around a given cluster, the cluster has about a 4 arc minute radius on average that it gives the sample. So you're looking at 50 square arc minutes. You're looking at about 1,500 galaxies per cluster. That's over about 8 arc minute by 8 arc minute region. And if you design the right instrument, which is, Mike has actually built this instrument called Gizmo, which basically is a multi-slice spectrograph. You can imagine trying to multiplex that for one of these 30-meter telescopes. You could do these 1,500 galaxies in either 1 or 2 passes. All right, so you can basically do each cluster in maybe an hour or 2 of total spectroscopy time, which is then how I get getting 3,500 clusters to get that down to about 100 nights of telescope time. So it is doable. It would require a very major commitment of resources by the astronomy community. All right. And in terms of improving your signal to noise of your final measurement, everyone's doing the photo Z's at 10 to the minus 4 level is the level you need to get down to so that the photo Z bias does not become the dominant noise factor. So we don't actually improve the signal to noise too much by going and getting very accurate spectroscopic ratios. Although, you know, the side benefits from this is we now have complete mass models for 3,500 clusters, so we can do mass evolution of clusters instead of trying to do the power spectrum evolution, right? Not quite as good, but again, better than nothing. We'll be able to compare these with the SZ and the X-ray surveys, so we can certainly get, you know, Steve Allen's method of using the baryon fraction to the strength of knowledge. So there's actually quite a bit to come out from this.
The range of scales your sensitivity is much more limited, right?
Well, in terms of this, right, I'm just doing pure tomography,
Yes, that's
right? The clusters themselves are just the old idea of using clusters as, you know, the mass tracers. Yeah.
Bradac,
Yeah.
I mean, I think this would be a really nice data set to have.
Right.
To do about it. I don't quite agree with your logic there. First, I would go over a factor of 10. The precision accuracy you need even for LSST snap is at the 10 to the minus 3 level, not 10 to the minus 4. The other is that to get that, you can ask you need what fraction of these galaxies do you need spectrum? I mean, you just made
Well,
the assumption.
yes and no, except
all
that
the galaxies.
because any okay.
Spectra for a million galaxies.
But if I go down to here, right, and let's take something snap. Okay, I can get spectra. Let's take the 30-minute telescopes. Let's say I can do 30 per square arc minute. All right. Of those, some fraction of those just won't have a redshift, right? It doesn't have anything even in the spectra to measure a redshift with. There's no way of taking those out of your photometric redshift sample, and you have no idea what redshift they are. So how biased are you in your photos?
Why isn't there a way of taking those out? They probably don't just probably sit in different places in color space than the ones you do get mentioned.
Not when you, because these number effectives which you're using, you're typically looking at signal noises of maybe 20 in you have a fairly large error, and that's going to push those into the regions.
Well, I mean, there's been a fair bit of effort that people are putting in, but I can certainly tell you that if you have a million spectra that you put a little bit of thought into targeting,
Right.
you can calibrate an all-sky survey that's getting you 40 or 50 galaxies per square mile easily to very fine accuracy. For snap, I mean, Gary can tell you a lot more details, but you need a little more to get at the faint galaxies or the far-away galaxies, and they're thinking about that. But just characterizing this problem that you'll get a million spectra and do clusters because you can't do this, that's not right. I mean, even a lot of people think I'm a few 100,000 spectra, not just
Okay, well, like I said,
spectra is just.
I disagree with you that I've become extremely pessimistic about photosynthesis,
Sorry?
just based on what I've seen from the results so far.
Well, if you, I mean, you're right that if you require the spectroscopic survey to be complete,
Right.
99 plus
Well,
percent.
it has to be complete in that every photo that you have in your training sample, you must be able to attach a spectroscopic redshift to it. Otherwise, you're going to be biasing yourself way too much.
Yeah,
Or
so
potentially biased.
if you're incomplete, you go and, I mean, to answer one question, if you're incomplete, it's okay if you can wall off that incomplete fraction with some color criteria, right? And excise it from the sample so that the remaining sample, which has some photometric criteria to define it, is 99 or 100% complete. That's okay, but I agree with you that, you know, whatever survey you go out to do, if you target 30, if you get 30 per square arc minute with successful redshifts, the density of those which will be in the sample that you choose will completely low. In fact, with 8 and 10 meter telescopes, you're never going to get, I think, above 10 or 12
Right.
galaxies per square arc minute in any kind of photometrically defined complete.
On that metric, how deep did GDDS go?
What was it, like 60%?
Well, no one's really gone into a tightly dense orbit, so or tightly dense passing spectra.
Because they pre-selected. So
Yeah.
Is the problem that you get collisions, or is it the problem of just
No
some of them being
lines.
too faint?
No, there's
Right.
lines. Yeah.
Don't see lines strong enough to pin a redshift on it. But, I mean, to be honest, I was thinking about doing the opposite in this year's survey, which is excluding the data in the vicinity of the clusters.
Right.
Because of this G gamma problem, and also because the weak lensing formalisms,
Oh, you definitely want to.
they have a calibration error in them.
You definitely have to exclude the cores.
And once the shear gets above 0.1, it's really hard to make an estimator that's accurate to a part of 10 to the 3, which is another thing that nobody's thought about that so much, but it is. So I was thinking of doing the opposite.
So if you just
Surveys.
Oh, anyway, as a possible just advertisement, just to end right quick. We do actually have a program underway now to try to look into some of this. It won't be nearly to the same accuracy, but basically Mel Ulmer and I have gotten money from the DOE just to do a sort of a trial run on this. In that currently the ACS has about 1/3 of a square degree of cluster. And so you take my simple scaling here, that's about 33 square degrees of the cosmic shear survey of tomography measurements. We do, about half of this has some level of ground-based colors, and most of these are just single color ACS images. So we do need to get something on the order of about 49 of CTIO or 8 on, LBT, so I'll come and ask Chris for some time soon. In order to get at least optical photoscenes from these. From this, we estimate we can at least get down to a DW of 0.3, although that isn't particularly interesting. More interesting would be to test this and see how good the tomography idea really is. All right. And finally, because of the vagaries of funding, we were told last week that we had this money. It starts in September and it starts for 1 year, and then it's potentially renewable each year. So if anyone knows of someone in the Chicago area looking for a job, let us know.
have to be counted.
And then, just remove.
Sorry. Any questions?
So the other piece of science that you lose is that because you're only probing geometry and not the growth rate, then you lose any sensitivity to testing gravity, the brain
Yes,
worlds or
yes.
whatever.
But you also lose the information that comes from the absolute level of the power spectrum.
Well, you get a little bit of that back from the cluster mass function change with redshift because you
Yeah. Right, but, you know, that there is distance information in the amplitude of the power spectrum.
Right.
And that's not involved.
How much can strong lensing tomography add to this?
Sorry?
Strong lensing tomography?
To be honest, haven't considered that. Of these clusters, the EDIS sample has a completely different result from the RCS. We only did about 10% of our clusters, 2 out of the 20 actually had visible strong lensing in the optical, at least in the VLT at least. So there wouldn't be a whole lot. Now, you go back and you get all this from space, then of course you have a whole lot of strong lensing around every cluster. But, you know, as we've also learned from the bullet cluster going out and getting the redshifts on the faint arcs, those are usually a little bit fainter than these galaxies that we're looking at. So,
And we're all redshift 2 as well.
yeah,
Yeah.
we're all redshift 2 and 3, which is much harder to get redshift. Yeah, but yeah, we do have hours and hours of Magellan exposure time on the bullet cluster arcs, all of which we can tell you are probably between 2 and 3 based on their lack of features.
So, I mean, generically, I agree with the statement you made, which is that the spectroscopic resources to support these large photometric programs, I don't think are clearly identified going forward. And I think we need to make progress on that.
Well, just to raise something that I'm surprised Doug didn't raise, but putting an infrared spectrograph in space is a really good way to make a more
Hellishly helpful.
deeper,
Yeah, well, you know,
redshift survey.
I'm saving my Destiny talk for Australia.
Yeah, and Destin is nice infrared spectrograph in space, and
Yeah, just
Snap
in
has
case.
a little infrared
Yeah.
spectrograph on it.
For those who haven't heard, we don't have as good of a PR machine as Snap. Destiny is, the idea behind it is it's a infrared only, it's 800 microns to 800 to 1.6. Sorry, 800 nanometers to 1.6 microns. It has, in its filter wheel, it will have both a filter and what am I allowed to call it? A spectroscopic unit. Yeah, that's one thing that I'm not allowed to actually say, is what it actually is. Which will, the idea is we get a smaller area, we don't go as deep as Snap, but what we do get is we get a R equals 75 spectra of every galaxy which we have an image of. That only about maybe 5 per square minute will we actually be able to pick up H alpha and get a spectroscopic redshift. But so for most of these, we'd be treating it as 10 to 15 narrow to medium band filters across that region, doing photos that way. So you think of it more as like a combo 17 photometric redshift instead of just the long band. So
If you were to put a spectroscopic unit in space,
Right.
you could see lines as well
Yeah.
as continuum features. I think you would blow away all the ground-based redshifts.
Yeah,
surveys
it's-
until somebody has a 30-meter telescope.
Yeah,
Yeah.
I think the spectroscopy is a solvable problem through some assumption of that. And what this comes down to, effectively, is making sure you can carry an absolute calibration across your survey area at the 1 carbon 10 to the 3. That's the real, the photometry. Because 1 magnitude is about a redshift of the easiest space to first order. So
Yeah.
that's how stable your calibration is.
That's another issue.
And that's actually a nice shot.
I think that's a separate issue that's also challenging, but just obtaining what is a calibration set. So,
That's
No.
just throwing money at some level.
well, a
And
lot of
looking through all this stuff up
30-meter
in the sky,
telescope is costing
it's
more than
less clear, to me at least, you can actually ever achieve that calibration stability.
1% is about scaling.
Right. You need to go a factor of 10 to 100 better than that.
Well, I will say this, that a fluctuation of your calibration across the sky, the spec for that would be significantly looser than the.
Well, it depends how you link the spectroscopy to the image. If your spectroscopy is scattered across your
Yeah, that's
whole
true.
survey, that's true. If it's, we did a deep survey here, and now we're gonna calibrate all of this
Right.
with that,
They
that
be
is
subject to one sample of the fluctuation.
So there's an interplay there that needs to be looked at. But the state of the art on calibration of photometry, boring as that sounds, is nowhere near where it needs to be.
Would you use much shallower spectroscopy across the field as a check?
Only if you can allow the galaxies to have the same temperatures.
In principle, possibly, yes. You could say, let me look at redshift half ellipticals and make sure I get nailed in down that. Of course, that's gonna check on some subset of your filters that give you the most leverage on redshifts of those kind of galaxies, the kind of redshift distributions you have for that kind of depth. So it won't give you everything.
If you're the SCD constraint analogy, is it boring?
That's their event.
So maybe this is really basic question, but supposing we want this 10 to the 5 galaxies to do the calibration so each year. Supposing these were all behind clusters, then that changes the overall magnitude of all the galaxies. But in
Well,
terms of colours, then is that still good for
In terms
calibrating
of,
photo Z?
in terms of the photo Z bias, and the problem with that would be you would have to get the magnification of a cluster down to extremely accurate levels.
Do you need to know the magnification? Because to get the photo Z, so you're just looking at the colours.
Yeah, then it goes to best ready. Maybe.
Red,
I
okay.
think the problem might be that the magnification would skew the redshift distribution of the sample, and you're making presumption, depending on how you do this calibration.
And yeah,
You might, if you're making the presumption that the spectra are being drawn from the same redshift distribution as the photometric galaxies, that would no longer be true because the magnification has redshift. If you just wanted to train some color neural net,
yeah,
then you probably need.
okay.
If you had an estimate of the magnification that was gives 10%.
Because what if you did, you possibly.
If you unmagnified the galaxy before you targeted them for the spectroscopy. Right, like to make a selection that's in a magnification.
Or really after take your spectroscopic sample, which is either it's been magnified and sort of the analysis gotten up a little bit.
So I keep hearing talks about needing 10 to 100,000 calibrations. Is the idea that we all apply for that time together?
Good question.
People at CAC will just give it to the birthday prince.
I think
Sarah's calling international collaboration. Spec of 8.
Well, I think, if you're proposing a project, NASA will not look kindly on you among other people for saying, well, here's this great project, we're everything we need. And when it's done, we'll just be waiting for somebody to do this, and then we'll publish it. Yeah, so you need to, at least for them, they like to see that you have a plan to get what you need to get it done.
But it could be the same time as
Yeah.
If you say you need boundaries of customers,
Well, they don't, first of all, you better show that it will happen. And second of all, they may not like having to
You
rely.
better say so half.
That's much better.
But for a lot of these big surveys, no one will.
But at least I have the commitment.
Yeah, but in the next few years, we not only have us needing spectroscopy to try to see if we can get the photo Z's to work, the SZ people need spectroscopy to get the redshift actually quite a few of these big spectroscopic surveys that need to be done. Unfortunately, we have to go a little bit deeper. than
There's
this.
no spectrum back.
Yeah, and there's nothing to do it down in the south right now. So.
So all these talk.
They don't need spectroscopy to be close to it. Photos easier to cross.
Well, on a shorter time scale, what's Pan-STARRS plan? I mean, are you going sufficiently deeper than existing spectral data sets? Are you worried?
I'm worried, yes. Yeah. I mean, the requirements are the same, so there isn't enough of data set that's.
No, yeah, but you're shallower than
Yeah,
Uber and DES.
Yeah, is your imaging depth deeper than the BVDS spectroscopic survey?
Well, so VVDS has got what, around about 10 to the 4.
Yeah.
So,
It's only 3.5.
yeah, and
It's hardly over the whole.
It's not very
spectrum.
complete at 24.
It's not, it's not enough, I assure you of that.
so now it's the fact that you're,
I mean, having 10,000 is not a factor of 10 worse than having 100,000. As far as the dark energy is concerned.
Yes, exactly.
The completeness of the EDS is more the worrying.
I guess, well, again, you would have to look at the BVDS sample and say over what color magnitude range is it complete to a high level, and you at least would have to back off to 23.5, right? And then there are fewer to work with.
You do have a plan for DES.
EDS is great. Great, okay. So let's thank Marusa and Doug again.
All right, so the plan for tonight is like to, so the restaurant is 20 minutes from here, walking distance, right? So the plan is to leave about half